This lecture will cover a family of problems which are particularly important in economics, which are optimization problems or constrained optimization problems. They are problems which involve taking a function that typically represents some real phenomenon and asking where it is minimized or maximized, quite often subject to a constraint or over a limited domain. So each of these problems will follow a general pattern. That's not to say that you'll do each of these steps every single time, but in general, you start off, these are generally all word problems. You will identify the objective function, that is, what is it that you are trying to maximize or minimize. You'll also write down any other important constraints, and you're going to substitute the available constraints into the objective function until you are left with only variables over which the person who is acting has control. So, for example, a farmer could not control the weather, but could control what crops are planted, how many acres she plants, and so forth. So you'll substitute the constraint into the objective function until and as many constraints as you have until you have a function that's only in terms of the actor's choice variables. You're then going to take the derivative of the resulting objective function, set it equal to 0, solve for the value of that unknown, that choice variable, and then test whether or not, make sure that if you're looking for a maximum, you actually found a maximum and not a minimum. And then check for a corner solution where appropriate. In other words, if you have a limited domain, you're not going to be interested in solutions to the problems that are outside of that domain. So, for example, if you're solving for how many widgets a company should produce, the company can't produce negative widgets, so you're going to eliminate any solution with a number less than 0. The key insight to these types of problems is to recognize that when you have a function graphed like this, any function, at either a local or a global minimum or maximum, the derivative, the tangent line at that point, is going to be completely flat. And the slope of both of those tangent lines is 0. So in general, what we're doing is if we have some objective function, we're interested in maximizing our objective function, f of x, with respect to x, we are going to find df of x dx, which will describe the slope of the tangent line for every point along this function, and then we're going to set it equal to 0 and solve for specifically the values of x where these minima occur. Because in these problems, we're typically dealing with choice variables, in other words, things that the actors are able to control. And so that's the general insight behind these types of problems. The rest of this lecture will be 3 separate optimization problem examples. I strongly encourage you to look at the problems, take a stab at them yourself before hearing me work through the solution. All right, so consider the problem, the following situation. Imagine you own a pear orchard and you know that you're able to keep planting trees and they generally will each yield about 400 pears per season, up to 60 trees on the land that you have available. After that, as you space the trees closer and closer together, the per tree yield declines by 4 pears on each tree for every additional tree planted. In other words, if you planted 10 additional trees, each of your 70 trees would yield 40 fewer pears. Okay? The question becomes, how many trees should the grower plant to maximize the yield? We know the answer is going to be at least 60 because the yields didn't start to fall before that point. But we're not sure at what point the decline in productivity balances out the increase in yield. So we're going to go ahead and ask what choices the farmer is making here. And the answer is the farmer is really choosing some number n, which I'm going to have be the number of trees over 60 that the farmer plants. The farmer is interested in yield, okay? So the objective function that the farmer has is that the farmer needs to maximize the yield, which is a function of n, by choosing the variable n. The yield itself is simply going to be the multiplication of the number of trees times the yield per tree. Okay, so to figure that out, we know that the farmer is planting at least 60 trees. Okay, and then we're going to add n to that for the number of additional trees the farmer plants. So if n were 10, this number would be 70. And then we're going to multiply that number of trees times the per tree yield, which we know is 400 minus 4 times the number of additional trees planted. Okay, this is simply a product that we can go ahead and FOIL to find the objective function. So I get y of n is equal to 24,000 plus 400n minus 240n minus 4n squared. And then I'll go ahead and combine like terms. 24,000 plus 160n minus 4n squared. So now my problem, since I'm trying to maximize the yield by my choice of n, is to take the derivative to find dy dn, which here I'm going to notice this constant goes away. Its derivative is 0. The derivative of the second term is going to be 160, and the derivative of the third term will be minus 8n. Now that's a generic derivative. It defines the slope of the tangent line at every point on the n-axis. I'm interested in just the maximum or the minimum, so in this case the maximum, so I'm going to set this value equal to 0. Okay. Sometimes you will see professors write it in this way as 160 minus 8n star equals 0 to basically signal to you that this is not a general solution for n, but rather for the optimum value of n. So I'm going to solve for that optimum value of n. I'm going to move the negative 8n to the other side, so I get 8n star is 160, or n is equal to 160 over 8, which is equal to 20 additional trees. I, at this point, have a few little housekeeping things that I need to double check. I need to verify that I've found that I've actually found a maximum, so I'm solving for the maximum yield here. The easiest way to do that with a polynomial is to take the second derivative with respect to n. So I'm going to do that. D squared y dn squared is equal to negative 8. That's less than 0. So I know that this is a maximum. Another way of thinking about that is that the function at that point is opening down, so the second derivative should be negative. I'd also at this point want to check that my answer was on a valid domain. So if I had come up with a negative number, for example, that would not have been a viable option. Similarly, if the farmer was liquidity constrained, only had the ability to buy 10 more trees, then I would have had a corner solution and the answer would have been 10 trees. which I know basically because the concavity of the function from that second derivative is negative, which means that on the region to the left, less than 20 trees, the value of the objective function is increasing, and so the corner solution would be the correct one. Last step, just make sure that I've answered the question that was asked. The question was how many trees should the grower plant to maximize the yield? And 60 plus 20. The grower should plant a total of 80 additional trees. All right, so here's another example. You may at this point want to just take a moment, pause the video, try it on your own. So this is a typical economic style maximization problem where we have a factory owner. The factory produces jeans. Her fixed costs every month are $500, and then she needs $9, or she has costs of $9 additional for each pair of jeans. From her knowledge of the market, she knows that she'll be able to sell jeans for a price that does depend on the number that she produces, so that the price is falling in the number that she produces. So this is a typical non-perfect competition where the choice of quantity affects the price of the good over the range that the producer is able to control. So when we think about profit, our formula for profit as a function of price and quantity is going to be simply revenue minus costs. We already know something about the price. In this case, we know that the revenue is going to be the price times the quantity, and that she has some fixed costs and some variable costs. If I think a little bit more about this cost structure, I have the price times the quantity minus the $500 fixed cost plus $9 for every jean that she purchases, that she produces. So that'll be 9 times the quantity. At this point, I need to substitute in the price. Now, this is just a quick change of variable. This was given to me with X as the quantity. I personally prefer to work with Q as the quantity just because it saves me from needing to interpret the results at the end. So I'm just rewriting this price, this expression for the price in terms of the quantity. Okay. So to answer A, I'm going to finally substitute in this expression for the price. I get 30 minus 0.2 times the square root of the quantity times the quantity minus 500 minus 9 times the quantity. At this point, I'm done, at least for part A, and I have an expression of the profit as a function, at this point, strictly of the quantity. I want you to notice, going back to the original rules that we started off with, I talked about an objective function and a constraint. And the constraint, in other words, the thing that the producer does not control, is she has no control over this relationship between quantity and price. That's set by the market, outside of her control. So what we do is we substitute that in. We know that we're going to want to maximize this profit function, and we substitute it in for the price, which she doesn't control, but we know that the price is a function of quantity, which is one of her choice variables. Okay, so now we're trying to figure out how many shirts she should sell to maximize the profit. So our problem becomes, or the producer's problem becomes, how do I maximize this pi function by my choice of quantity? Okay, it's probably worth doing a little bit of additional manipulation over on the right-hand side of the formula before taking the derivative. So I'm going to multiply this out. I get 30q, and I'm going to switch to using a fractional exponent because as I multiply, that makes it easy for me to add the exponent. So I have 1/2 plus 1 gives me q to the 3/2 minus 500 minus 9q. And then final step, I'll just combine like terms and get 21q minus 0.2 q to the 3/2 minus 500. So now I'm going to take the derivative of the profit function with respect to the producer's choice variable q. And I'm just going to work off of this expression over here. I take the derivative of the first term with respect to q. I get 21. I take the derivative of the second expression. I have 0.2 times 3/2 times q to the 1/2. And then the derivative of the third term is 0. Now I'm interested in optimization, so I'll simplify this a little bit and set it equal to 0. So I have 21, I'm going to multiply these out. 0.2 divided by 2 is 0.1, so the coefficient is 0.3, q to the 1/2, and I'll just put a little asterisk there to remind myself that this is just the optimal value of q, not a general solution for q. I'm going to move the q term to the right-hand side and then flip the order of the terms so that I have 0.3 times the square root of our optimal q is equal to 21. This is 3/10, which is also, and then I'm going to multiply both sides by the reciprocal, 10/3. So I get the square root of our optimum q is equal to 10/3 times 21, or 210 divided by 3, or 70. And that makes our optimal q 70 squared. I'm going to then take the second derivative, just coming back up here, and I see that the coefficient on q is negative. I bring down the 1/2. So as I work over here, d squared pi dq squared, the second derivative of the profit function with respect to q, the first term goes away. The second term was 0.3. It was negative times 1/2 q to the negative 1/2. The sign on that is negative, so it's less than 0. So this function is concave down at that point. It has a negative second derivative, and this is a maximum. So this quantity, 4,900, is the producer's profit maximizing point. The final two questions, if I just go back up and make sure that I'm actually answering all the questions that were asked, we were asked at what price the shirts would sell and how much profit she makes. So I'll go ahead and just erase a few things here. And we can plug in our solution to this expression for the price. Okay, we got 4,900, or 70 squared. So the price is going to be 30 minus 0.2 times the square root of 70 squared, or just 30 minus 0.2 times 70, or about 30 minus 17, which is $16. So the jeans are she makes them for $9, she's going to sell them for $16. And her profit, we can look at our original profit expression over here, and we would plug in for the quantity 4,900 right there. This isn't something that I would give you on a test where you couldn't use a calculator. In this case, you would end up with the profit at a production point of 3,900 would be $33,800 per month. Finally, our last example problem is another standard economics profit maximization problem. It's a great time to pause the video, give it a shot. So here we have just a generic producer who's making widgets. However, you have a maximum number. Your production capacity is 800. You cannot make more than 800 in the time period we're considering. So we're going to look at your profit, okay? And just generically, your profit is your revenue minus your cost. And under almost all circumstances, your revenue is going to be your price times your quantity, and your cost will be whatever it is defined by the problem. Okay, so in this case, we are already given the revenue. They've already plugged in whatever the dependence between price and quantity is. So we have that the revenue is 5Q minus 0.003Q squared. And we're subtracting from that 300 plus 1.1Q. Okay, so here we have an expression in Q, a quadratic in Q. We're going to combine the two terms. Notice that this negative sign will distribute in. So I have, combining the two Q terms, I have 3.9Q minus 0.003Q squared minus 300. I'm going to do the standard approach, take the derivative of the profit with respect to the choice variable, Q. Okay, in other words, the problem that we're solving is we're going to maximize the profit through the choice of the quantity produced. That derivative, working through the process, I get 3.9 minus, bring the 2 down, 0.006 times Q, and then the derivative of the last term is, of course, 0. I'm going to set that equal to 0. I'll use Q star just to indicate that this is the special optimal value, or at least extrema value of Q. I move the negative term to the other side and flip them around. I get 0.006Q is equal to 3.9. Just for ease of working with everything, I'm going to multiply both sides of the equation by 10. I get 0.06Q is equal to 39. Okay. I'm going to rewrite, just because I'm doing this math on the fly, rewrite this as a fraction because it's going to make it easier for me to do the necessary multiplication, which is I'm going to multiply the entire equation by 100 over 6 and get that Q is equal to 3,900 over 6. And doing that division, I get 650. I get a quantity of 650. I want to double check by taking the second derivative. I take the second derivative. The second derivative of the first term is 0. The second derivative of the second term is negative 0.006, which is less than 6. So we have found the solution of 650, which will be the number that we're going to produce. The last thing I need to do is double check for any corner solutions. This is a positive number. I'm great. I also, in this case, was given an additional constraint, which was that Q had to be less than 800 or less, and my solution meets it. But if it had not, because the second derivative is less than 0, that maximum value would become what I produced. And there you have it.